Alright, welcome to a new day. Let's go and finish up these slides. So we learned about a lot of stuff last time, like variables and all the types involved. We remembered our types, assignment statements, division, including integer division, which is horrible sometimes, and the inner workings of chars and strings. So we ended on a cool example, and now it's time to talk about types some more. All right, I want to talk about how much stuff you can put in a type, which will get into like sizes and binary and cool stuff like that. We love powers of 2 in this class. All right, so here's a big table that I don't expect you to understand yet. I'm going to do my best to explain it, and I'm going to show it to you again after I've gone over what I'm trying to go over today. All right. So here are some sizes of some types. All right, so integers, for example, they are 4 bytes long, and 4 bytes corresponds to 32 bits. All right, it's okay if you've never heard those words before. Don't worry, I'm going to explain them soon, but I want you to hear them first. All right, and that means that integers with all this space, they can hold numbers as small as this, negative 2 to the 31st power, all the way to positive 2 to the 31st minus 1. All right, so that's the range of values you can put in an int. For a char, you only get 1 byte, and that corresponds to less space, less numbers that you can put into a char. It can't hold anything bigger or smaller than those. Doubles are stored in a weird, fancy way, but they're 8 bytes long. All right, so that's a lot of space, and they store their numbers in like scientific notation, and so you can have really tiny numbers all the way to really big numbers, but you only get a few digits of precision. It's stored in some sort of binary scientific notation that you'll have to wait until CSCI 45 to understand fully. But that's what a double is all about. There is another type called a float that came first. That's also a type that holds decimal places, and floats are 4 bytes long, and that's why it's called a double, because it's double the size of a float. But that's another type that you can use one day. And then we have other integer types. So short and long are fun ones. So a short type is half the size of an int, can hold these numbers, and a long, which is weird, is double the size of an int, and it holds whole numbers again. So it's kind of, see how like the exponent is kind of doubled in a sense. All right. So this is a table. You've seen it. You've heard me speak these words that may not make sense. Let's make it make sense now. Like what is a byte? Let's go from first principles now. All right. So we are not going to program for a little while today, because we need to talk about bases and base conversion first, and then that'll get us into bytes and stuff like that. All right, so let's learn something called base conversion. All right, because I need to teach you binary now. So all of the numbers that we know and love as humans are written in base 10. So that's also called decimal. All right, our numbers are decimal numbers, and we also call that base 10 because we have 10 digits that we use to build up our numbers, right? 0 through 9, 0, 1, 2, all the way to 9. That is 10 digits total, right? Before you need a new place. 10 digits total. So that's nice. Interesting. All right, so those are the numbers we get to use when we're making numbers as humans. There are other bases, though, like base 5. That's a thing. You can make numbers in base 5, and that means which digits do you get to work with? You get 0, 1, 2, you only get 5 digits, right? 0, 1, 2, 3, and 4. And you got to build up your numbers with those, which is interesting to think about. And so it's like a whole different number system in that sense. And because we're talking about number systems, I need to specify now which numbers we're using, which base we're using. All right, so this is 100, the number that we know and love, and I'm going to mark that with this subscript 10 to mean this is the decimal base 10 100 number that we know and love, because that's not the same as, because I can also say 100 in base 5, right? That is not the same as 100 in base 10. It's a smaller number. This is actually 25. All right, so I'll get you up to speed on how to like do the translation, but these are different number systems, and I'm going to use subscripts to talk about which base we're using right now. All right, so there's a bunch of different bases. Maybe if you lived in the Simpsons world, because they have 8 fingers instead of 10, we think that we use decimal because we have 10 fingers usually. So maybe if you lived in the Simpsons world, you'd be using base 8 for your numbers, only going up to 7. All right. So binary is a very special base to us computer scientists. We call it base 2, and that means we only get 2 digits to work with, 0 and 1. And we have to build up all the numbers in the world with just 0 and 1. So that means, all right, let's start counting. 0 is 0, of course. 1 is 1. And then if we want to make 2 in binary, the number 2, how can we represent it? Well, we've run out of space in one digit. We have to add a new place. So 1, 0, that means 1, 0 in base 2, that equals the number 2 that we know in decimal. Do you kind of understand how I'm doing this subscripting? Does it all make sense? So please yell at me if this is at all confusing, but that's what binary is all about. And that must be the number 2 in binary. And that means like 1, 1 is the number 3. All right, so we can represent any number in any base, but it's going to look different. All right, so now that we have binary, we can talk about spaces, all right, and just like space usage. So a binary digit, a single binary digit in a binary number is called a bit, all right? So they just took this letter and these letters and shoved them together and called it a bit instead of saying binary digit all day long. And so you can talk about how many bits is in a number that's in binary. So like this is 1011 in binary. That is a 4-bit number. I haven't told you what number it really is yet. You can try to figure it out before I teach you the technique. But that's a 4-bit number, so it took up 4 binary digits to represent that number. And a byte is a very important unit of space in computer science. That is 8 bits. Any number made of 8 bits is called a byte. All right, so 8 binary digits. So let's make up a random byte, 10110011. So that binary number, whatever it is, that is 1 byte long. All right. Cool. And so the smallest, therefore, byte is all zeros. And then the largest byte, 8 zeros, followed by all the way down to 8 ones, right? That's the biggest byte. And this happens to be the number 255. You'll start memorizing these things once you see them enough. So, okay, we've talked about these different bases. Like, how do you know what number this really is? Because we think in terms of decimal. How do you get it back to decimal? All right, let me show you how to convert it. And so there's going to be a trick, and it's going to correspond to a trick you already know with decimal numbers, all right? So let me show that to you first. So you remember how, like, in grade school, you were taught how to break down, like, a large number that's just a normal decimal number, so 1,234? Let's break it down. You were taught this, right, in, like, elementary school. Like, 1,234 is 1,000 plus 200 plus 30 plus 4, right? You remember that? And then once you got to like middle school and learned about powers or something, then you learned that you could break this down further. This is 1 times 10 cubed, right? If I can draw my digits correctly. Plus 2 times, let's try to line these up, plus 2 times 10 squared, right? Plus 3 times 10 to the first power. Plus 4, you can still do it times 10 to the something, but it's got to be 10 to the 0th power. See that? And notice, do you see the secret? Notice where the base appears. There's base 10 number. It's the base 10 number. Do you see where the base appears? Boop, 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 and boop. Interesting. That pattern corresponds in any other base. You can do the same kind of way to break it down, and like if you just do the math in decimal, then you'll get whatever decimal number it was. All right. So usually you start, like if you're doing this backwards or doing this from an arbitrary base, you'll start with this number. Like you'll start from the 4. Like do this one, and that's the 10 of the zeros place. This is now the 10 of the first place, stuff like that. So you're going to start with the rightmost digit. All right. But let's do that now. Let's go through that process for a binary number. All right. And so I hope you can imagine how the base is going to change. It's not going to be 10s all over the place. It's going to be 2s. All right. So we'll start with the rightmost digit so that we can align it properly. This is 0. 0 times what? Following this pattern. 0 times, not 10, but 2, that's our base. 2 to the 0th power. We always start at the 0th power. It's the ones place for any base. And then plus a 1 times 2 to the what? 2 to the first power, right? This is the 2's place. See that? Because 2 to the 1 is 2. All right. And then we got plus 0 times 2 squared, right? It's the 2 squared's place. Plus 0 times 2 cubed. I'm having trouble writing my 3's today, sorry. And then plus another 1 times 2 to the 4th. And of course you didn't need to write out the zeros, it's just, I'm doing it in full for you to see it once. All right, so this is, simplifying, it's 2 to the 4th plus 2 to the 1st, right? Which is 2, 4, 8, 16 plus 2, right? And that means it's 18. That's the number 18 in decimal. This is that. Just a different number system. It's a different base. That's how you convert, all right? I hope that makes sense. So you try. All right, here is 1111. This is the biggest 4-bit number. Please convert it to decimal. That's your binary number. The biggest 4-bit number in binary, convert it back to decimal in that same style, please. All right, please, please, please do pause these videos. It's the way that you learn. You got to stop and try it. So let's do these in order. Let's start right from the rightmost bit. That's 1 times 2, not to the 1's power, but to the 0 power, right? 2 to the 0's place first. And now this is the 2 to the first place, so it's 1 times the power there, plus, now this is the 2 squared's place, and we see a 1, so it's 1 times 2 squared, and then 1 more, right? Plus 1 times 2 cubed. And so that's going to be equal to 8 plus 4 plus 2 plus 1, and if you do the math, that is 15. So the biggest 4-bit number is 15 in decimal. Cool. All right, I hope that's starting to sink in and make sense. That is, that's the secret. So now you know how to go that way. What if I gave you a number in decimal and I told you to convert it to binary? That way is unfortunately much, much harder. All right, so pay extra attention to this part. So let's say I give you this number, 1,234. How do you extract the binary digits, the bits from that? All right, and so just like for this pattern, there's going to be a pattern that I'll teach you first in just normal decimal. All right, let's come up with an algorithm to extract just not the binary digits, but just the decimal digits out of 1,234. Let's try to get the 4 out, the 3 out, the 2 out, and the 1 out. All right, from this number, there's going to be an algorithm, and I'll show that to you, and it's going to generalize to binary too. All right. What we're going to need for this algorithm is a new operation. This exists in C++, by the way. I'm going to use the % sign to represent it, because that's what we're going to use in C++ when we use it. So it's called the remainder operation, or modulus. I'll pronounce it as like modulo as a verb, or mod for short. But this % sign means do the remainder operation after dividing. All right, so if I said I'm going to do this, if I write this out, you're going to read it as 10 modulo 2, or 10 mod 2 for short. And what that means, it's going to calculate a number. It's like % sign looks kind of like division, but you're going to do the division and then give back the remainder. So 10 mod 2, you're going to do the division. So like do 10 divided by 2. What is that? That's 5. And then it's 5, and it goes in cleanly, right, with remainder 0. Remember learning that before you learned fractions? So like that's what the answer is. The answer is 0 for 10 mod 2. That's the remainder after dividing by 2, because it's even, there's nothing left over, and so it's 0. See that? And so if you do modulus by a certain number, there's a way to get out always the rightmost digit of a decimal number. All right, to get that 4 out, do you see what you might be able to modulo by? There's going to be a trick here, all right? And the trick is the base. So 1,234. Do you see how if you did mod 10 on this, right? Because if you divide 10 into this, right? 1,234 divided by 10, that's 123.4. But if you did it in the old grade school style, it's like 123 remainder 4, right? You remember that? There is your 4. You can extract the 4. So that's the first step of this algorithm. So I'm just going to teach you how to extract the decimal digits of a decimal number. Then we'll learn how to extract the binary digits of a decimal number. So you start with your number, and you can pick out the rightmost digit of that with mod 10. All right, do you see how that's going to give you the 4? Because it goes in 123 times with 4 left over. See that? And then now, all right, I now have a way to always get the rightmost digit of a number. If only I could do something that will give me 123, right? If I could do some math that will give me 123, then I can keep playing this game, right? Then I can get the rightmost digit with mod 10. I can get the 3 out, then make it smaller. Chop off, right? I'll chop off the 4, then I'll chop off the 3 to make 12, and keep getting the rightmost digit. Do you see that will eventually give me every digit of the number? So like, all right, what do I do here? What's the secret? I've actually already written it. If you do the division without the remainder, that gives you the 123. Do you see that? And we have a name for that kind of division that chops off the remainder, don't we? Scrolling back up. That's another reason we learned this. It's integer division. If you do integer division by 10, that will give you what we want, all right? So integer divide by 10, chop off all the decimal places. That will give you 123. And now you can keep on repeating this game. All right, 123, extract its rightmost digit by doing mod 10. So it goes in 12 times with 3 left over. There's the 3. Now I want to chop off the 3 out of 123, and I'll do integer divide by 10, right? It's 12.3, so we'll chop off the 0.3. There's my 12. And now I'll get the rightmost digit of 12 in decimal. That's 12 mod 10. Gives me the 2, right? It goes in once with 2 left over. Then I'll chop off the 2 from 12 by doing integer division by 10. That's 1, right? And then I'll get the rightmost digit of 1. This is an algorithm, we're not sure. I'll show you like the stopping condition. The rightmost digit of 1, well, try to divide 1 by 10. It goes in 0 times with 1 left over. All right, chop off the 1 from 1. 1 integer division by 10. That gives me 0, all right? And once you hit 0, then you know you're done. There's no digits left, all right? So that's our stopping condition. And notice, every time I took a modulus, I got the remainder, I got a digit of this number in reverse order, right? So it's 1, 2, 3, 4 in that order. You see that? So this is that's a way to extract the decimal digits of a decimal number. To extract the binary digits of a binary number, do you see what you might change? I hope you see this pattern. That's the base we want to go to. So if we replace these guys with 2's, we will extract binary digits. See that? And chop off binary digits, chop off bits. Cool. So that works for every base. Definitely a bit harder, but that's the process. So what you're going to do is you're going to keep dividing and taking the modulus by the base you're trying to convert to. So instead of 10 everywhere, if you're going to binary, it's going to be 2. All right. So let's convert 15 in decimal to binary because we know what the answer should be. We can check our result. All right. So the secret is you start with a number, and then you're going to extract the rightmost bit of it, the rightmost binary digit. So it's 15 mod, the base we're trying to go to, which is 2 this time. All right. 15 mod 2. That goes in like 7 times with 1 left over, right? An easy way to do mod 2 is just like look at the number. If it's odd, it's never going to go in cleanly. There's always going to be remainder 1, okay? And by the way, you know this is going to work, at least a sanity check is what are the possible remainders after dividing by 2? It's either 0 or 1, and those are the only digits you can use in binary. So like that's helpful, right? That's telling us that we're on the right track. So, okay, 15 mod 2 is 1. So the rightmost bit of 15 in binary is 1. All right, that's what we know now. Now we want to kind of like chop off the 2 in 15 somehow. All right, chop off the 1, the rightmost bit in 15. All right, so we're going to do 15 integer divided by 2. Give me the smaller number that if I convert it to binary, then I'll have my answer. All right, so 15 integer divided by 2, that's 7, right? Because it's 7.5, you chop off the 0.5. And now I just need to convert 7 to binary, tack a 1 at the end, and I'm done. All right, so 7, what's its rightmost bit in binary form? 7 mod 2. Again, it's odd, so it doesn't go in cleanly. It goes in with 1 left over, right? 3.5, 3 remainder 1. And then, all right, I've got the 1 bit out. Let's chop off that 1 somehow out of this 7 in binary land, and that's going to be 7 integer divided by 2. All right, that gives me 3. And then I'll just keep playing this game. What's the rightmost bit of 3 in binary? It's odd, so 1. Then chop off the 1, so integer divided by 2. That makes 1, right? Because it's 1.5. And then, all right, now I have 1 to work with. Let's convert 1 to binary. 1 mod 2, what's its rightmost bit? It goes in 0 times with 1 left over, and then 1 integer divided by 2 to chop off the 1 to see if there's anything left to do. Gives me 0, and that's how I know I'm done. All right? And so I guess it doesn't matter because it's all 1s in this case, but every time I took a modulus, I got a bit, right? I got a digit back, and it's in reverse order. So this is the rightmost, second to rightmost, third to rightmost. This is like the first bit, all right? So that's the answer. You read it off this way, all right? So keep that in mind. And so that means, all right, 15 in decimal land is equal to 1111 in binary. That's our answer, all right? And we know that's correct. I hope that makes sense. Please do come to office hours, yell at me if you have any questions about this stuff, but that's the trick, all right? And now it's your turn. All right, so here's a number, 117 in decimal. Please convert that, not to binary, but to base 5, all right? So you're going to follow this pattern. Instead of modding by 10, modding by 2, try to figure out what you're going to do there. Base 5 is what you need to go to, all right? And that means the digits involved, the numbers that you get to use in base 5 are 0, 1, 2, 3, and 4, right? That's all you get. So, all right, follow this process, follow this pattern, see if you can do it. All right. right, and then once you have your answer, remember that you can check it very easily, because that's the easy way. You can always go from a base back to decimal using this power expansion. So you know immediately how to check your answer on a test. Okay, so it's 117 in decimal to base 5. I want the rightmost base 5 number, base 5 digit, and so that's 117 mod 5. I guess the trick is, like, the closest multiple of 5 is 115, and it's 2 more. So 2 is definitely going to be the rightmost digit in base 5 land. Then we want to chop off that 2 by doing integer division by 5. 117 divided by 5. I do not know the answer off the top of my head, but I can use Python to tell me. 117 divided by 5 is 23 if you do integer division. 23, and then what's 23 mod 5? Because we now need to convert that to base 5, right? And then tack a 2 on at the end, and we're done. So 23, what's its rightmost base 5 digit? That is going to be a 3, right? Because it goes in 4 times to make 20 with 3 left over. Okay, that's 3, and then chop off the 3 in the base 5 representation by integer dividing by 5. That goes and gives me 4, right? And then, all right, now I have 4. Let's convert 4 to base 5. So 4, what's its rightmost base 5 digit? 4 mod 5 is goes in 0 times with 4 left over. All right, and then we'll chop off the 4, see if there's anything left to do. For integer divide by 5, that's 0, and so we're done. All right, and so that means our answer is, every time we took a mod, we got in a digit in reverse order. So it's not 2, 3, 4, it's 4, 3, 2. 4, 3, 2 base 5 is going to be our answer. And we can check that, right? It's very easy to check that because we know how to go the other way. So, all right, how do we do this, right? How do we go back to decimal? It's going to be, all right, 2, right? 2 times 5 to the zeros place, plus 3 times 5 to the ones place, plus 4 times 5 squared. That's the 25s place, I guess. So, all right, 4 times 25 is 100, 3 times 5 is 15, and then 2 times 1 is 2. That looks like it's checking out. That's 117. Base 10, of course. Cool, and so that's a very easy way to check your answer. All right, so definitely to get to some other base is the harder direction, and that's the one you'll have to study a bit more. Okay, so I hope that makes sense, and now you have some cool knowledge. All right, we can go back to programming stuff now. We're ready again. So hopefully this table makes a lot more sense now, and you can kind of get a feel for why, like, you have a bigger range for integers rather than chars and shorts and things. So, all right, every int, for example, is 4 bytes long, and that's 32 bits because there's 8 bits in a byte. All right, and so that means, like, the smallest int, for example, is 32 zeros. Every time you write a number, it's taken up all 32 bits. So if you have the number 0, it's 32 zeros. I haven't shown you how to make negative numbers, but you can kind of hopefully understand that, like, why it looks like almost 32. Okay, we're kind of giving up some positive numbers to make negative numbers. And then, like, the biggest, in a sense, int is 32 ones. Right, so that's 32 digits always for an integer in binary. It's either got a bunch of zeros on the left side if it's small, or ones if it's big. All right, so that's integers, and now you know, like, you can kind of see why chars are so small. You can only hold 256 different values. That's right, 2 to the 8 or whatever, because you get 8 bytes. Okay, so I haven't shown you again how to make the negatives, but we're kind of like giving up half the space to make negative numbers in a sense. All right, doubles are weird. You'll have to wait till a future class to understand how they are represented. But, like, that is, you can kind of hopefully understand this table a little bit better now. All right, and so I do want to say, like, the number 0 in binary is all zeros, 32 zeros, if it's an int, if it's stored as an int. If you have the number 1 stored as an int in, int x equals 1, secretly, right, if we're going to look at this in binary, what does x look like in memory? It's secretly 32 bits long. It's got a 1 at the end, right, because that is 1 in binary, is the same as 1 in decimal. But it's got 31 zeros, because it's making up 32 bits. So it's just padded with a bunch of zeros, essentially. 0, 0. So there are 31 zeros in the number 1. 31 zeros, okay? And then a 1 at the end to make 32 bits long. So that's what I'm trying to say. All right, I hope that makes sense. That's how they're going to be stored. If you don't need all the digits, you're going to pad it with zeros. All right. So I think we're ready to go to programming now. I want to teach you about constants. All right. This finally makes the assignment statement in C++ kind of look like an assignment statement. So I'll show you what const is. So const is just a word you can put before any type when you're making a variable to make it a constant. All right. And so you're kind of forced to give it a value when you make a const, but it becomes a constant variable after that. Const just means constant, and you cannot change your variable as you could normally when you mark it as const. So like for pi, for example, that's a good candidate for making a const variable because pi never changes, right? So if you say const double pi rather than just double pi, instead of that, you say that, then you're not allowed, like it won't even compile. You get a compiler error to if you ever try to change the value of pi in your code. So that's really nice and very useful. So try to make all your variables const as much as you can, the ones that don't need to change. So let's make a new file called const.cpp, and I'll show you that. So here, like, all right, const double pi equals 3.14. So instead of doing it like this, like that's our normal double variable, let's put const at the front, and now that's going to mark it as a constant. All right, so pi is a const variable. You can't change it now, which is very, very nice. So if you try, it won't even compile. If I try to do this, like, all right, pi is now 3. I try to compile this. It's like, nope, assignment of read-only variables. So constant makes it read-only. You can never change it. You cannot write to it ever again. So that's pretty nice, right? Now you cannot accidentally mess up. So that's super, super cool, and I encourage you to use const as much as humanly possible. So you can't do silly stuff like this now. So that's great. So that's const, not too hard to explain. Now let's talk about functions, because I showed you this before. We talked about like when we were talking about strings, for example. There are operations that strings know how to do for us, like the .at, for example. That is an example of what's called a function. Secretly, it's called something else, but like in essence, it is a function. All right, and so it's just code that somebody else wrote and made for us to use. It was in the library, right? Same with like the set precision that we were using when we were printing stuff. Where was that? Yeah, this guy, set precision. We gave it some numbers, right, around parentheses, and so that was all calls to a function, right? So I want to teach you some new terminology. So when you use somebody else's code, you're using their functions that they've made for you. That's just something that they made that you can call, right? It's the metaphor is like you're shouting out to it, asking it to do something for you. So you're asking this function with a name to do something. And functions, they take 0 or more things called arguments in between parentheses, and they're comma separated, all right? And so that, oops, what have I done here? There we go. So those just kind of change the way the function does its thing. So like you call it with certain values, you give back a different answer than if you called it with different values, essentially. All right, and so yeah, functions usually give back an answer. They're going off and doing something for you. They usually give back their result, and when they give back an answer, you get to pretend that your call to the function is going to get replaced with that answer. So, all right, that was a lot of words. I had to say the words first. Now let's give examples. So it looks like this when you call a function. You say its name, and then between parentheses you give arguments. So, for example, there is a function called sqrt, which stands for square root. All right, that gives you the square root of a number, and you say it like this. Here's how you call the square root, sqrt, and then you put between parentheses what it needs. Square root needs an argument. It needs to know what you want the square root of, right? So you give it like 2.0, for example, and then that gives back, right? It goes off. You called the function with 2.0. It's going to give you back as the answer the square root of 2. And that's like, it's going to give you back like 1.41 whatever, right? And so this you get back, you can kind of imagine that somebody's typing out the answer for you. Somebody's typing the 1.41 where you called that function. So like you can give this to cout, for example. Cout the square root of 2, semicolon, like this is going to turn into 1.41. It's going to give me that answer back, and it's going to print that. Okay, so that's what a function call is all about. some other fun library functions. There's one called pow, short for power. So it's like it gives you back some number to the power of some other number. So like 2 to the 3.55 power or something. You can get at this by calling pow, and it's going to need 2 arguments, right? Then the number that's the base and the number that's the exponent. So you do it in this order. It's the base first, then 2 to the 3.5. That's how you call pow. And then that'll give you back whatever the answer was. All right, that's pretty cool. Another cool example is rand. Rand is short for random, and it will give you back a random number, a random integer. So you call it just by itself. It doesn't need any arguments, and it will give you back some random number. It's usually something giant that you'll need to shrink down, usually. But like maybe you call it and it gives you back that. But if you call it again, it gives you back a different number. All right, so it doesn't need any arguments because it's just like, all right, you wanted a random number, here you go. But like these guys, they need to know what you need the square root of, what you want the power of. All right, so let me show you that in code. These functions live in different places. So it's cstdlib and cmath. Cstdlib stands for C standard library, by the way, and cmath. So CMath stands for the math library. These are from the C language, though. These are libraries from the old version of the C language that we get access to. And so you are going to get very, very acquainted with this website, cplus.com. It has documentation on what lives in these libraries. So you can go to this link, or you can just search for, like, all right, C++, cstdlib. And, like, the first link is going to be that website. All right, so here it is. And you can see all the functions that live in the cstdlib library. So here's what you get. That's where rand lives, for example. Which ones do I want to do first? Let's do cmath first, because like all the math functions kind of make sense to be all together. And then cstdlib has a bunch of random stuff here, including random itself. So here's cmath. There. So here are all the math functions that you get, like sine, cosine, tangent, all the stuff that you would want to have. Exp takes a number, e to the power of something. You got the log. You've got logs with different bases, log base 2. There's pow, pow and square root. There they all are. And then there's some other cool ones, and I want to show you a few of them. Let's see. If you want to know more about any of these guys, you click on them and it'll take you to a page with an example and then also some more information. But here is like square root, for example. Let's click on square root. Let me show you how to read this stuff. So when you click on it, it shows you this. This is something that you'll learn more when I teach you how to make your own functions. But this is very, very interesting and important information. So you can read this all in one line, and it's kind of telling you what square root's going to do and what it takes. So you read it like this. Square root is a function that takes one double as an argument, and it gives you back a double. The very first thing is the type that it gives you back. That's the square root, and I hope that makes sense. And like there's an example below. So that's kind of cool and useful. What else? Like pow takes 2 things, and here's how you notice. Like, all right, pow is a function that takes 2 things, the base and the exponent, and those are doubles, and it gives you back the double result. Does that make sense? And then, like you can read the text and see the examples, but like that's how you understand this. Okay. So I hope that makes sense. And so let me show you some of these. So let's do cmath first, and I'll show you some of the math functions. So if they live, though, in cmath, I better include cmath in order to use it. So I'll make a new file called mathstuff.cpp. And so I'll include cmath, and then I'll make some calls. So I'll be like square root. Please give me the square root of 2.0 and see out the result. So you get to assume, like, it's going to give you back the answer and like it's going to replace it with where you called it. And so that'll print out then the square root of 2. Boop. And so there it is. Beautiful. Isn't that nice? What are some other ones I want to show you? Exp. Exp is a function that gives you back, well, it takes a double, gives you back a double, and it gives you back e to the power of that thing. So e to the power of whatever that you give it as that exponent. So like if I wanted the number e, the constant e, I can call exp with just 1, because that'll compute e to the first power, right? And so that's an easy way to get e. You can store that in like a const variable or something. So let's try that. See out the result of calling exp with 1.0, or just 1, because it'll be converted to a double as you call it. That's not an issue. So there's E. Cool. All right. I think you can understand how PAL works. I won't show PAL, but let me show you a couple other interesting ones. Let's talk about rounding. All right, I want to talk about rounding. And so like there's a normal round function. Where's that? Let me just search for it. It's called round. There it is. There's round. That rounds to like the closest number. But there's some other kinds of rounding that I want to show you. All right. There's one called floor and there's one called ceiling. That's a cute little metaphor. So floor takes a double and it rounds it down to a whole number, even though it still gives it back to you as a double. And then ceiling rounds a number up. Again, takes a double, gives you back a double. So let me show you what that means. So let's say we got the number 2.15. If you give that to ceiling, it's kind of like you're pushing up the number to the ceiling. It's going to give you the closest whole number that's bigger than this guy, bigger than or equal to. So that's 3, right? It'll give you back 3. That's what ceiling does. That's the kind of rounding. It's like round up always, even though it's only 2.15. It's ceiling always rounds up if it's not already a whole number. And then floor, it's like you're pushing down the number to the floor. It rounds it down always if it's not already a whole number. So that'll give you back 2. All right, does that make sense? So that's a little weird, but those are going to be useful one day. All right, so I'm showing them to you now. So now you can understand, right? Ceil of 2.15 is going to give back just 3, right? Going to give back 3, though as a double. It'll give it back to you as a double. You can store it into an integer, though, if you wanted to, because that's very quick and easy to convert. It's always going to be a whole number that it gives you back. What next? So then like floor, right? It's going to always round down. That's going to 2. That's going to give back 2. And it's always going to give back 2. It's always going to go down. So even if you gave it 2.99, the floor of that, shoving it down to the closest whole number, is still 2. All right, that's a little weird. If you want the normal rounding, that's the round function. That's the normal rounding that you get from math. So that's round to the nearest number. So like round of 2.15 will give you back 2. That's the round function. And then round of 2.5 will do the normal math class rounding and give you back 3. All right, so that's the one you're going to reach for the most probably. Let's do round of those as an example. 2.15 and then round of 2.5. That's the normal rounding. So there's 2 and 3 as you would expect. All right, but ceiling and floor are useful. All right, so those are some math functions that live in the CMath library. And then let's talk about rand. All right, that deserves its own slide because it's a little complicated. Okay, so random numbers, and we'll make a new file for that too. To make random numbers, it lives in the cstdlib library. Let's go back to that. So here's rand, you click on it. Rand is a function that takes nothing, the void, takes no arguments, and it gives you back an integer. That's how you read it. All right. And so I encourage you to read all this. It's going to give you back a giant number. All right. Usually it gives you back a random number between 0 and some constant called rand max. All right. Whatever that is. Depends on the computer you're running this on. But that's what it does. So rand gives you back a random number between 0 and rand max, which is just some large number. All right. So we can actually print out what is rand max for our machine. So let's do all that. Rand.cpp. That lives in cstdlib. And so I can now say, hey, what's rand max? That's just a constant defined in the library. And it happens to be the largest, on this machine, it happens to be the largest positive integer. So that's perfect for us. Awesome. So it's going to be a big number usually when we call rand. So if I see out, like, let's call rand a few times. Rand. That's going to give me back a random number between 0 and rand max. It's always a non-negative number. And there they are. Those are my 3 random numbers that I'm printing out. See how it's different every time you call it? And now, all right, let me rerun this program. So it's going to print out rand max and 3 random numbers. Well, I mean, technically, that's possible with randomness. It's just very unlikely. Let's try it again. I have a feeling something's going wrong here. All right, so it gives me back the same 3 random numbers every time. What is the problem? What is happening here? All right, so the issue is rand. It is a pseudo-random number. It's not a perfectly random number, even though it kind of functions like one. For all intents and purposes, in this class at least, it's going to give you back what you can think of as a random number. But secretly, it's doing some math to calculate the next random number. It's really got a sequence that it's using. So like, it starts off with, let's say, the number 1 that starts off the random number, like by default or something. Like that's the first number that starts off the random generation by default. And then it uses that to generate the next random number in just like a weird way that looks random to humans. All right, so like maybe it uses 1 to generate 42, and like that's the next random number. And then if you ask for another one, it's going to use the 42 now to generate the next random number. It'll make like 85. So it's got like some random sequence that it's making. And maybe it uses that one. If you ask for another one, to make like 12. And so like it's generating a random sequence, but if you know how it was doing it, it's not random secretly. It though looks random though to users of the library. All right, and so the issue that we were running into is like we kept using the default value every time we called rand. Like we started with the default number in the sequence, like it started at 1 or something, and so that means we were getting the same random numbers. That's not what we want. All right, so there's a way to change that starting value of the sequence so that like it can have some other random sequence of numbers that it generates, and so that'll look actually random to us. So rand, therefore, we say it needs to be seeded. We want to seed the random number generator. Plant the seed of some random number inside of it. All right, so that will let it then produce a sequence of different random numbers each time. All right, and so what we want to do is every time we run the program, we want to give a different starting value so that we get a different sequence of random numbers. And so a good candidate for a number that's always going to be different every time we rerun the program is the current time, right? Because time changes as we run the program. So here's what we do. We can seed the random number generator with a function called srand. That seeds the random number generator with some starting value for its sequence, for its random sequence. And a good starting value is the time converted to a number. So in the ctime library, there's a function called time that we'll call with a 0 argument, and that will get replaced. This will give back the current number of seconds since midnight on January 1st, 1970. Don't ask me why they did it that way, but like that's the number we can get back by calling time. And we can give that to srand, and so every time we run our program, it'll be a different value. That'll kick off the randomness in a new, cool way. All right? So that's what we need to put at the start of our program. Before we ask for random numbers, we want to seed the random number generator with the current time. All right, so moral of the story, srand time 0. Because time 0 will give back the number of seconds since 1970, and so that corresponds to the current time, so that's going to get replaced with that number, and then srand takes that number and seeds the random number generator with it. So seed the random number generator with the current time. And so now, after all that work, all that explanation, I get 3 different random numbers. 3 different random numbers. 3 different random numbers. That's what I want. Okay? These are very large and unwieldy. Usually you're not going to do it that way. You're going to want like a random number between 1 and 100 or something. So let me show you how to do that. All right. So let's figure out how to get a random number between 1 and like something that the user wants. Like we don't even know ahead of time what they want it up to. Like maybe they ask for a random number between 1 and 10, 1 and 100. Let's figure this out. All right. So here's the secret. All right. The secret is going to involve the modulus operation. All right, something that we know already. It's going to be able to shrink down our random numbers, right? Because by default, when you call random, it's going to give you back a number between 0 and this bad boy. That's a big, big number. If I say rand and take that number and shrink it down with the modulus, mod something, let's do like 10 first. What's it going to do? Well, it's going to give me back that random number, and it's going to shrink it down. What are the possible remainders after dividing by 10? Those are 0, 1, 2, all the way to 9, right? Does that make sense? That's what's going to happen. So it's going to shrink it down, and I'm going to get a random number within this range now. And so if we wanted a random number up to the user's choice, like n, let's say that the user's choice is called n, we'll start with doing rand mod n. That's not quite what we want though, right? Because it's going to give me back a random number between 0 and what now, if it's mod n? 0 all the way to, what are the possible remainders after dividing by n? 0 all the way to n minus 1. See that? So it's almost there. It's a little bit off though. We want a sequence that's random between 1 and n, not 0 and n minus 1. But do you see how I could fix this? Like, take whatever random number I just got, and as long as I add 1 to it, what I'm getting back, right, is then going to be a number in the right range, between 1, 2, all the way to n. All right, so that's the secret. That's how you take your big long number that Rand gave you back, and you shrink it down to be a random number in a range that you care about. So let's use that. Let's ask the user, hey, give me a number, and then I'll give you a random number back from 1 up to that number. Enter a number, make room for it, get it with cn, and then I want to calculate a random number between 1 and n. All right, so, and then I'll see out whatever that was. So what goes here now is a call to rand, right? There's my random number, and then I would like to shrink it down to be not from 0 to giant number, but from 0 to n minus 1, right? That's the first step. I'm going to do rand mod n. So now it's a number between 0 to n minus 1, random number. If I add 1 to that, then I get a random number between 1 and n. And that's what I want here. So enter a number 100. So now I'm getting 90, for example. If I rerun it, give me another random number up to 100, I get 7 now. So it's perfectly random. It's perfect. It's beautiful. And then you can have smaller examples. Give me a random number from 1 to 10. 2. Again, 2. That's technically possible under randomness. Now it's 8. All right. Give me a random number from 1 to 2, like either 1 or 2. It's 1 this time, 2 that time. Cool. So you see the idea. All right. So that's the trick there. Let's also use this to output 3 random characters. Won't that be fun? Because what is a character? What's a char but a big number, right? Really a small number. So let's use rand to make a random char. So what are the valid values of ASCII characters? So it starts at 0, and it goes all the way up to, the ASCII table goes up to 127. So if I want a random number between 0 and 127, what do I mod by? $128. See it? So, all right, there's my random character. Give me a number between 0 and 127. That is an int. It will be converted on the fly to a char, though, because it's small enough. It's small enough to be there. So that's a random character. Let's do 3 of them. And then we'll print them out, and we'll see if they're actually printable. Because a number of those characters in the ASCII table were like unprintable characters. They weren't things that humans can see. So I'll print them out all next to each other and then a new line to end them off. Let's do it like that. So that'll be fun. Let's see. Let's see what happens. It's like a Ouija board. Let's see here. I have to type something in there. And then apparently it was some like space, maybe either space or an unprintable character, and then a capital T and then a $sign. Cool. And then this time it was EA and an unprintable character. Let's see if we can get 3 printable characters. There we go. Cool. That was what the universe is telling us right now. Interpret it as you see fit. So that's pretty cool. All right. I think that's what I wanted to say there. So randomness is useful. That's how you make games, right? You can have the monsters going in weird patterns thanks to randomness. And so randomness is a very, very useful concept. That's why it needed its own slide. So yeah, I think to end us off in terms of content, let's talk about the operations that you can do on strings, because they're essentially function calls, but they look a bit different. All right. So if I make a string, we know what that looks like in memory now, right? If I say string s equals hello, it's going to secretly look like this in memory. You can access each character, right, at an index, and you can use the .at to get at them. So H-E-L-L-O, so here's where they all are, H-E, 2 L's and an O. H lives at index 0, E lives at index 1, all the way to 4 for the O. All right, so that's where they all live. And so the string library, there is a page on that here. It's like, it's in other, I think. String, you can click on the string type, and then here's all the operations that you can do on a string. You can get its size. You can do .at to get a character back. So these are all operations on a string that you give. So you have to say the name of the string you're calling the operation on first. So it's a little bit different to a function call. It's really called a method. All right, it's like .find will go and look for a character. It's like, what's happening here? Like this kind of syntax, the .at, the .size. It's called a method call, really. All right, we'll learn more about that later, but you can think of it like a function right now because it's really just a function, just a fancy different kind of function. It's called a method in that it acts on the thing you put before the dot. So like the S is kind of like an argument in a sense. It acts on S. It's like, hey S, tell me your size. That's kind of how that works. Instead of like putting it in the center there. So it's a different school of thought in a sense. All right, so yeah, let's talk about these. So s.size, for example, that's a method call. It's like a function on strings, and it will tell you about how big that size, how big that string was. And so it's got some weird things that you'll learn more of later, but it's like you call it size, and it gives you back just a big long integer, takes no arguments, of how big that string was, and it gives you back in a type that looks a little weird. It's called size t. You can think of it like an int, though. It's a number that can be converted into an int. So that's what size does. It just tells you how many characters were in that string. How many chars? So there's 5 in hello. And let me prove that to you. So if I want to do string stuff, I need to include the string library. String s equals hello. There we go. And let's output, hey, string s, what is your size? It's kind of like you're asking it to do something for you. You're asking the string s, tell me your size, please. Boop. And so it is 5. It's telling you how many characters are inside of it. Another cool thing, another operation on string, it's not like a function call, but secretly it turns into one, if you want to think about it that way. You can do plus on strings. So because the types are different, it's not going to do numerical plus. What plus on strings does is it combines 2 strings together. So it generates a third string that is it's called the concatenation of the characters in each string. So it's just it's going to add them all together, add the characters all together. So let's make another string, like comma space world, exclamation point. How about that? And then let's make a third string. String combo is s plus s2. I think you can imagine what's going to happen when I print that out. It's going to be a third string that holds all the characters hello, comma space world. Yeah. So there's that. Find. Find is an operation on strings that gives you back the place where it finds that character. So let me show you that. Find content in string. Again, these are kind of hard to read, but like the example is kind of useful. But we're going to use it in this way. Find, give me, I'm looking for a character. I'm not going to give a second argument because it gives a default value. We're going to keep the default value, and it's going to give me back an index. All right, so as an integer, essentially, an index. It's easier for me to just show you. All right, so you say s.find h. What it's going to do is going to give back the index where it finds the first h, all right, inside the string. If it finds it, it'll give you back the index of that thing. So let's take our hello string and be like s.find, where is that h? And what it gives back is essentially an index that you can use. Let's call it an int. So index of h is whatever that gives me, all right? And then there's L's, right? I'm saying that it's going to give you back the index of the first L, so 0, 1, 2, if you ask for it to find an L for you. So this is going to give back 2, and I'll show you that. And then let's see what happens if you ask it for something that's not there. Index of like a Z. Let's ask it to find a Z, and there is no Z, of course, in that string. So let's output these. we'll space separate them on the same line. All right, let's see what it says. So yeah, the index of the h is the 0. The index of L is going to find the first index, so that's 2, 0, 1, 2. And then if it doesn't find your thing, it gives back -1. And that's perfect, right? Because -1 is an index that can never exist. Your indices start at 0. So if you ever see -1, that means it didn't find it, all right? That's how it signals that to you. And then, yeah, let me show you the rest of these. They're a little bit fancy. So s.replace is cool, but it's called in a very weird way. So s.replace, you call it on a line by itself. This one doesn't give anything back. It just does something for you inside of s. So what it does is it replaces len characters out of s. So like you give a number here, how many characters you want to replace, starting at this index. So starting from this index, replace this many characters, and so like delete that many characters, and in its place, put the contents of this string s2. So you're given 3 things. You call it on a line by itself, and it does that. All right, that makes no sense in words. So let me show that to you in code. So let's see. Let's say what I want to do. Here's my goal. Let's convert. Let's do like English to Spanish translation. Let's convert hello, the string, to hola. All right. So let's take our s and replace. What do I need to do to get hello and turn it into hola? I would like to keep the h, but everything else goes away, right? The lo needs to go away. So I need to replace, that means 4 characters, right? I want to replace 4 characters starting with the e, which is at index 0, 1. So e is at index 1. I want to replace 4 characters there, so like chop off the 4 characters, chop off the lo, and replace them with ola. See that? You don't have to give 4 characters. You can give something smaller or bigger. It doesn't matter. But it's going to, all right, starting in index 1, that's this. Get rid of the 4 characters that are there, chop off 4 characters, and replace those 4 characters with whatever I put here. Sorry, not old, but hola. Excuse me. And now that's going to change s. So you call it a line by itself. It messes with s, gives nothing back, but it changes the string. So now s holds hola. All right, perfect. I hope that makes sense. It's better with an example, right? And then substr is short for substring. This one gives back a brand new string made out of a piece of your string s. So what it does is it takes len characters from s starting at index start. All right, so it's like, go, hey s, give me back a piece of you, without changing s though. Give me back a piece of you starting at this index and take that many characters. So let me show that. Again, an example is worth 1,000 words. So let's extract. Let's say I've got my hola, right? My string s holds hola right now. So let's say that I want to get the la out of it. Let's extract la from hola. Okay? And so I'll make a string called la. Why not? Because it gives back. It doesn't mess with s. It just gives me a piece of s, and it doesn't change s itself. So it's like, all right, from s, which holds hola right now, I would like a substr. I'd like a piece of you, please. And I would like, starting at, like, where's the la start? It starts at index 0, 1, 2. That's where la starts. So starting at index 2, give me back 2 characters, right? That's L and the A. So give me back 2 characters starting at index 2. That will be la. All right, and that does not mess with s. So s is still there, did not change. So there's my la, and it kept s intact. Okay, beautiful. So that's some string operations that are very useful, and you will need them one day. Let's see here. So yeah, I think what I want to end on now, we made it to the end of these slides. Congratulate yourself. I would like you to tell me now, think of the difference between, just pause the video, think about this, think long and hard, because it's a very important difference. There's a few differences, in fact. What are the differences between 1, 2, 3 and double quoted 1, 2, 3 when they're in code? All right. What does this mean? What does this mean? What are their differences? And try to write down a list of all the different differences, right? A good hint for you is to think about what you can do to this and what you can do to this in code, all right? Because the operations are different, aren't they? This is a very, very important thing to think about. It's a common mistake, actually, to conflate the two of these. All right, so let me show you how I might think of this. So definitely try it first, though. Try it yourself, because that's how you learn. So, right, what are the difference between the two of these? So, okay, 1, 2, 3. That is a number. Right? That's a number. If you put it into a double, it could be double. If you put it into an int, it's an int. But like it's an int without anything else. You can think of it as an int. So it's a number for sure. This, though, is a string, isn't it? So the types are different, first of all. And then what can you do to a number, right? What can you do to just 123 by itself, like that, as an int, for example? Well, you can add it to other numbers, subtract, multiply, divide. You can do math stuff with it and give it to pow, take the power of it, make it the exponent as well. There we go. You can give it to square root, ask for the square root of that number. You can't do any of that with a string, can you? You can do plus on strings, but it gives you a completely different plus, doesn't it? Right? So you have to be very careful. If you got a number in text form, you gotta like convert it to a number if you need to, because like 123 plus 123 the string plus 4, 5, 6 the string. That gives you, right, 1, 2, 3, 4, 5, 6. It does not do math. It just puts characters next to each other. So that's the plus you get there, which is maybe not what you want. And then you do get all the other string stuff. You can get like dot size, which is actually nice on numbers. Like you can get the digits very easily with dot size. It's harder when it's a number. You got to do like the digit extraction process to figure out how many digits are in that number. Dot subster. You can do that on strings, right? But not ints, of course. Dot at, you can go very quickly to an index of this string, which is sometimes useful, right? It's hard to get at an index of this number, right? Get at which digit? Again, you'd have to play that game of moduluses, chopping off things like this, okay? So like there are pros and cons, but there's a huge, huge difference in terms of what you can do, all right? There are ways to convert between the two. I'll show you that later, but make sure you're working on the right one, okay? Make sure it's what you expect it to be, because you will run into issues if you try to do math on strings, for example. All right, sometimes it won't even compile. So I think that's all that I wanted to say for the day. We've finished these slides. We'll be ready for some new ones next time. So yeah, do yell at me if you have any questions about anything. But if you don't, I will see you in the next one.